So as we move into Learning Unit 3, we really start to kind of get into what many may have experienced in a high school chemistry course, kind of talking about the mole and doing reaction stoichiometry and balancing chemical equations and limiting reagents and all that fun stuff. So this is going to be a rather meaty chapter, some very important basic skills that we will use throughout the course. So this is a really important chapter to master. And so the first thing that we're going to talk about, there's 4 skills total in this learning unit, is talking about the mole and chemical formulas. So the mole is really how chemists count things. The mole allows us to relate quantity and mass. And again, it allows us to count things. So it tells us the number of items that we'll have in a given mass of a substance. So 1 mole of any substance is going to contain what we call Avogadro's number, 6.022 times 10 to the 23rd. That's a number you're going to want to know how to use. You don't need to memorize it. I will provide it for you, but that is Avogadro's number. So 1 mole of a substance contains 6.022 times 10 to the 23rd items. So we can use some information from a previous skill. So we learned, if we're talking about molecular weight, that a molecule of water would have a mass of 18 atomic mass units. Remember, we got that from adding up the individual atomic masses of 2 hydrogen atoms and 1 oxygen atom. So again, that's going to be 18.02 atomic mass units. Numerically, it's going to be the same answer when we start talking about a mole of water, which is going to be Avogadro's number of molecules, is going to have a mass of the same numerical value, but different units. It's going to have that mass in grams. So nothing different in terms of how we determine it. It's now just going to have units of grams per mole. And we define this as molecular weight or molar mass. You'll see me abbreviate it using M with a little sub W for molecular weight. We can apply this to covalent compounds like we have with water, or again, we can use it to think about ionic compounds. For example, table salt is sodium chloride. A formula unit of sodium chloride, so that's going to be 1 sodium cation and 1 chloride anion, is going to have a mass of 58.44 atomic mass units. Again, that's information you get from adding up the mass of 1 sodium cation and 1 chloride anion. Mass is on the periodic table, and we get to 58.44 atomic mass units. When we talk about having a mole of sodium chloride, so 6.022 times 10 to the 23rd formula units, now that's going to have the same numerical value, but just different units, 58.44 grams. So when we talk about molecular weight or formula mass or molecular mass, we're going to be doing the same thing, adding up the individual masses of elements that we find on the periodic table. The only thing that's different is now the units are going to be grams per mole. So why is this something that's useful? Well, we're beginning to start to accumulate unit conversions that we can use in chemistry. So unit conversion, that dimensional analysis skill that we learned in our first learning unit, is going to continue throughout the entirety of this course. But what's going to happen now is we're going to start having unit conversions that are chemistry related. So there's 3 that we're going to discuss on this slide here. The first is using that molecular weight. Remember, anytime you have a weight or a quantity that has 2 sort of units to it, for example, density is relating mass and volume. That's a unit conversion that allows us to walk between those 2 units. So for example, molecular weight, having units of grams per mole, allows us to interconvert the mass of a substance with the number of moles of that same substance. And again, we can go in either direction with this. Now, I'm not going to have you guys remember, if we go in this direction, we multiply, in this direction, we divide. Just use unit conversion. You will be able to then figure out whether you're multiplying or dividing, and you won't make a mistake, I promise. So molecular weight is going to be the bridge between moles and mass. So if we have the mass of a substance, we can convert that to moles of a substance using the molecular weight. Again, I might use interchange terms, molecular weight, molar mass, formula weight for ionic compounds. They're all referring to the same thing. Add up those individual atomic weights from the periodic table, and you're going to have the molecular weight or the formula unit weight for your covalent or ionic compound. Avogadro's number is going to be a unit conversion that allows us to change between the amount of a substance that we have in moles and the number of items that we have. So maybe the number of formula units or the number of molecules. So if we're talking about the number of molecules we have, it's usually going to be a big number if we're talking about something that's kind of tangible that we could sort of weigh out or measure. So we've got molecular weight, we've got Avogadro's number, and then the third piece is something that it's not quite obvious, but it allows us to change the amount in moles that we have of a compound with the amount, for example, of elements within the compound. So I'm just going to do a quick example here just to highlight. There's three sort of substances I'm going to use throughout sort of this little learning skill, things that are in your everyday world. We're going to talk about table salt. We're going to talk about glucose, which is part of table sugar, and we're going to talk about water. So for example, let me talk about water here. Water is H2O, okay? And if we have 1 mole of water, that means we are going to have 1 mole of oxygen atoms, but 2 moles of hydrogen atoms. So the chemical formula allows us to change the amount in moles of the total compound to the moles of individual atoms or elements within that compound. So glucose, I'll just kind of put it up here. We're going to talk about this, is C6H12O6. Nothing you need to know. We're just going to use it as an example. This is glucose. If we had 1 mole of glucose, there would be 6 moles of carbon, 12 moles of hydrogen atoms, and then 6 moles of oxygen atoms. So that's, again, just information we get from chemical formula. So now we've just learned our 3 unit conversions that allow us to change between moles, mass, number of items, and then amount in moles of elements or atoms within a compound. So lots of problems to practice using those unit conversion pieces. The next thing that we're going to talk about is, and we've already sort of mentioned this, there's different kinds of formulas that we can have for the compounds that we make. And we're going to relate this to both ionic and covalent compounds. And I'm going to, again, talk about the 3 different substances that we've already sort of been mentioning. The first we're going to mention is sodium chloride. So the empirical formula for sodium chloride is going to be NaCl. Again, this shows us the relative number of atoms that we're going to have in a compound, and it shows us that there's 1 sodium cation for every chloride anion. So let's talk about water, H2O. In this case, we've got 2 oxygen atoms for every 1 oxygen atom. So empirical formulas are going to be in what we call the simplest whole number ratio. So I'm going to abbreviate this a lot so I don't have to consistently write it out. SWNR refers to the simplest whole number ratio. So empirical formulas are always going to be the simplest whole number ratio of all of our elements. So what we have for glucose, the simplest whole number ratio for all the atoms in glucose is actually going to be CH2O. Okay? Again, if we flip back here and look at what we had, this was the chemical formula for glucose, but I can divide everything by 6 and get everything in a 1:2:1 ratio, which is what we see here, a 1:2:1 ratio. So the empirical formula for glucose is going to be CH2O. Now, molecular formulas show the actual number of atoms in the compound. So when it comes to sodium chloride, there's actually not a molecular formula because it's not a covalent compound. So molecular formulas really only apply to covalent compounds. And remember, covalent compounds are only created when we combine two or more nonmetals. Okay? So in this case, we do have water as a covalent compound, but the actual number of atoms in water is still H2O. So water is an example where the empirical formula and the molecular formula are identical. Now what we have for glucose here, the empirical formula is CH2O. The molecular formula gets scaled up to what we had on our previous slide and reminds us that every molecule of glucose has 6 carbons, 12 hydrogens, and 6 oxygens. The last little piece here is not anything that's going to be really important for you to know here, but I just want to highlight what we're going to get to towards the end of the course here is thinking about sort of the structural formulas that these molecules have. And in this case, we really don't have a structural formula that we want to think about for an ionic compound. All ionic compounds or salts exist in what we call crystal lattices. And that's really just a big cube, if you will, that has alternating cations and anions. We'll get to those details actually not till the second semester of general chemistry. But let's talk about what we have for structural formulas for water and for glucose. And I want to highlight here, you do not need to know this. But I just want to show you it as a way to think about how we will begin to think about structures of molecules towards the end of this course. Water is actually going to look like this, and a structural formula is actually going to show us who is connected to who, and it's going to show things like electrons and all kinds of good stuff like that. So that's how we draw the structure of water. You will be able to draw water by the end of the course. One that you won't learn in this course, but you may get to in future courses, is I'm going to draw the structure here of glucose. So the structure of glucose basically has a lot more atoms, so there's a lot more options for how we might draw that structure. Again, don't worry if this is really complicated. That's not anything you need to know about, but I just wanted to highlight that structural formulas show us the actual connectivity of different atoms in a covalent compound. All right, so the last sort of important skill in this sort of initial opening piece to our third learning unit is thinking about how we determine both empirical and molecular formulas. So when we're determining an empirical formula, I'm going to sort of give you a roadmap that's going to be consistent. Okay, the first piece, and I'm going to write this roadmap in this first section here, and it'll actually incorporate all 3 of these steps. The first step is to determine the mass of each component element. So we're going to have, for example, the grams of substance X. Okay, we're going to convert that mass to the amount of moles using the atomic mass. So I'm going to just draw in my roadmap, I'm going to call this the atomic weight, and that's going to give me the moles then of X. Now we're going to do this for each substance that we have within our compound. So maybe we'll have X, and then maybe we'll have Y, and then maybe we'll have Z, depending on however many different substances that we have. What we're then going to do is we're going to write a preliminary formula. And how we're going to do that is we're going to have some ratio of X, we're going to have a certain number of them, Y, and a certain number of them, and then Z, and a certain number of them. So when we get these moles of X, Y, and Z, they're not likely to be whole numbers. So what we need to do is we need to divide each one of them by the smallest number. And this might not make sense until you do a few problems, but what this is going to do is whatever one is smallest, that's going to end up with a subscript of 1. Everything else will be a larger number, and hopefully it'll end up being whole numbers so that we have an empirical formula, which is again the simplest whole number ratio of all of our species. So again, once we get to this ratio here, we're going to ask the question, is this the simplest whole number ratio? And if it is, then we're all set and we're done. Something else we might need to think about is going to come on the next page here when we think about if something is a covalent compound, it has a different molecular formula. Okay, so when you're determining empirical formulas, take the grams of each element that you have, convert it to moles of each element using the atomic mass, take the ratio of all of those moles and get it to the simplest whole number ratio. That will be your empirical formula. All right. Well, what about a molecular formula? Well, if you have an ionic compound, there's only going to be empirical formulas. It's not a molecule, so we're not going to have a molecular formula. So again, ionic compounds in our example here, when we were talking about sodium chloride, that's all there is. There's nothing more to do. There's only an empirical formula. So we don't do anything else with ionic compounds. But for things like covalent compounds, right, for our two examples here with water and then with glucose, the empirical formulas that we have might not be the stopping place. Now, again, for water, we know that it is going to be the empirical formula is equal to the molecular formula. But for glucose, the empirical formula as the simplest whole number ratio of those atoms is not the same thing as the total number of atoms that we find within a molecule of glucose. We need to scale that up. So reading these directions here, for some covalent compounds, the molecular formula is going to be a whole number multiple of the empirical formula. So again, if you know the molar mass of a compound, we can use the empirical formula to kind of obtain that information. So I'm just going to run through that as an example here with glucose. So for example, the empirical formula was CH2O. If we were to figure out the molecular weight of this, we would get that that's 30 grams per mole. And just to remind you how we get that, it's 12.01 for carbon, plus 2 times 1.008 for hydrogen, plus 1 times 16 for the oxygen. Add all of those up, and we get to 30 grams per mole would be the molecular weight of a compound that is CH2O. Well, we know, for example, with glucose is going to have a molecular weight of 180 grams per mole. And when I say we know that, there's experimental data that you might be given that tells you that. If you know that the actual molecular weight of your compound is some scaled up version, that tells us the scaling factor that we need to scale up by. So our actual molecular weight is 6 times what the molecular weight is for the empirical formula. So what that means is I know that I need to scale up my empirical formula by 6. That means every atom gets multiplied by 6. So we're going to have C6, H, 2 times 6 is 12, O6. And if we went and determined what the molecular weight of that is by taking 6 times 12 plus 12 times 1 plus 6 times 16, that will actually get us to this 180. All right, one more slide here. I know this was a little bit of a longer video, but chapter 3 is probably one of our most intense sort of learning units here. So the level of complexity that you're going to have for these, molecular and empirical formula determinations is dependent on how directly information is given to you. Okay, so I'm going to kind of come back here and I'm going to copy this because I want to have this little piece of information be part of what we have here. The simplest is where information is given directly to you. So the simplest problem that you'll have, maybe even the simplest problem, is starting right here. You're given moles of different substances that might be, or elements that might be in a compound. You just have to figure out the simplest whole number ratio. That gives you the empirical formula. That's probably the most direct way. In reality, the simplest problem we're going to see, I'm calling this a level 1, is you're given the grams of a substance and then you need to use the atomic weight to get to moles, simplest whole number ratio to get to our empirical formula. Now we're going to go through one example in class, and then we've got challenge problems that are kind of this third level. I'm not going to go through those in class. There's information kind of on your handout here for how to do those kinds of problems. I'm going to just kind of highlight it here. It is something that there's a video problem on how to do it. It is something that you might see kind of on an exam, but it is an intense sort of problem because we back up quite a ways in terms of the amount of information that's given to us. So let's see if we can understand how we would do a level 2 type problem. Okay? A level 2 type problem means we're given not mass data, but mass percent data. So we might say that a certain compound has, 12% carbon and 15% oxygen, and the balance is bromine, let's say. Okay, what we would have to do then is use a phrase in every 100. So I know I talked about this in a previous skill. In every 100. What that allows us to do is take any number that's given as a percent, and you just take that same number and you write it with units of grams. So for example, in our last, what I was just saying there, if we said something was 12% carbon by mass, you could say, all right, I'm going to imagine I have 100 grams of this substance. 12 grams of that is going to be carbon. And once I know the grams that I have, now I'm starting out like I'm a level 1 problem. So it's just a little bit extra work to understand that percents can be converted into grams by making the assumption and saying the phrase in every 100. This is a really important skill that's going to have application beyond just this. When we have percents don't have units. But if we say in every 100, we can convert it into something that has units that we can then use. Okay? Just going to introduce how this challenge problem works. It's just one more step removed to get us to mass amounts. Okay, so this is what's called combustion analysis. And really what it means is we've got carbon and hydrogen and at most one other element. So we're only going to have 3 elements in our compound that we're going to be analyzing. And what happens is this problem is going to give you carbon dioxide data, it's going to give you water data, and then we're going to need to do a little detective work to convert that into carbon grams, into hydrogen grams, and then into the grams of whatever else was left. So I'm going to walk you through it. Remember, this is a challenge problem. This is a little bit intense. So you're going to get carbon dioxide mass data. Now, how some of these problems are set up is you actually might have to do a little subtraction work in order to figure out what's the mass of carbon dioxide. How this actually works is you have something that's called a carbon dioxide absorber in your experimental setup. You're going to have the mass of the absorber before your experiment, the mass of your absorber after the experiment. So the difference between those two masses is going to be the mass of carbon dioxide that you made in your experiment. So we're going to have carbon dioxide mass. Carbon dioxide is 12 grams of carbon in 44 grams of carbon dioxide. So this is one of those ratios that tells us if I have carbon dioxide, I can take the molecular weight of carbon dioxide is 44.01 grams, and I know that the molecular weight of carbon is the amount of carbon that's in there. So this is essentially our unit conversion that converts mass of carbon dioxide into grams of carbon. I'm going to do the same thing here for the mass of water. But this time, the mass of water is 18.01 grams of water, 2.016 grams of hydrogen. You'll notice that this is actually twice what the periodic table tells me, but that's because there's that 2. That's why that's there. But this little unit conversion is going to get me to grams of hydrogen. So now, essentially, it's like I'm starting at a level 1 problem. But there's one little other trick I need to do. Remember, there was 3 elements that were in our compound. Using carbon dioxide mass will give me grams of carbon. Water mass will give me grams of hydrogen. So the mass of the other substance is going to come from this little piece. I know the total mass that I started with, and if I subtract my grams of carbon and I subtract my grams of hydrogen from what I started with, remember one of those laws that said we can't create something out of nothing? The rest of the mass must be that other substance. So the remainder equals the grams of what other element we have as part of our compound. We can only do this kind of analysis if we have 3 elements in our compound. Carbon being one, hydrogen being one, and then something else being the other element. Okay, so this is kind of a challenge problem, but for those of you who are up to the challenge, I encourage you to try to work through some of these combustion analysis problems to determine both empirical and molecular formulas. I know this one was a little bit long, and they're probably going to be a little bit longer here for chapter 3 because this information is kind of intense for this learning unit.